So now let's go to the Stokes theorem. We want to see a recap of what we have talked about in the Stokes theorem before we proceed with the applications. Right, so let's look at the first one here. So for the Stokes theorem in 2 dimensions, here is the equation where you relate the integral between the curl of the vector v, and you dot it with k that is in the direction that you want, normal to the surface, and then you relate this to the integral of the vector v along a closed line. So just to show you an example, I make a simple plot like this, where this is on my xy plane, and this d sigma over here is basically the small area of this boundary, which is written as the partial derivative of a. Right, so here this partial derivative of a is to show that this is the boundary that we are talking about, that we are interested to evaluate the integral, whereas this d sigma is the integration of dx dy. So when you extend this to 3D, it looks something like this, where here you have double integral over here, the same, and this is the opposite of the divergence theorem, because in divergence theorem you actually add another integral when you go from 2D to 3D, but here it looks exactly the same with just some minor changes. So if you look at here, this is a integral over the area, whereas in the 3D this is the integral over an open surface. Curl v dot k over here, this is n, so n, this is the area, the unit vector normal to the surface, and then here this is the same expression, except for now instead of a partial derivative of a, you have partial derivative of sigma, and this sigma is just the component of the area, right? So this is the Stokes theorem. Let's go now to the next slide. So here we want to talk a little bit about the relation between the curl of the vectors and the fact that this shows the tendency of the vector to rotate. So if you look at the discussions in the book, you will see that they first talk about the problem that we have looked into earlier, that is on the rotation of an object about an axis. So in this case, if we talk about for example, the angular momentum, we have this as over here the z-axis, and you have a particle which rotates about the z-axis, that is, you are rotating on the xy plane, and we have found that when you take the omega cross with r, you will get the linear velocity of the object, right? So here, now as you go along here, then you want to ask, what happens to v? Is v going to be constant, or is v going to change? So now if you evaluate the curl of the vector v, so the curl of the vector v is now written like this. So the v is equals to omega cross r. So if you put it inside, and then you just have to recall the expression for a triple vector product or cross product, and you will see that you have a cross b cross c with a bracket over here. So you will remember that the b should be the first term on the right, and then the other two components is going to be a dot product of these two. So you have a dot c, and then the second term you will have the vector that is at the back of the bracket, which is c here, and the terms that is entering here is the remaining two, which is a dot b. So if you apply this expression into this equation here, you will see that this is going to be omega, and here is the del operator dot with the r, and the remaining one is r here, and you have del dot omega. Right, so what you need to do next is to expand this. So for the first term, you have a del over here, and you're going to take the dot product with respect to r, which is written like this, and you must retain the omega over here. And the next term is just the del dot with omega. So not omega, this omega is a vector, so you need to write it in terms of the ijk components. And here I will leave it to you to do some simple exercise. Basically, you'll have to show that this integral is equals to 3 omega, and the second integral is going to be equals to omega. So then you have the curl of the vector v, when this v now represents the velocity of the particle, is going to be equals to 2 omega. So here it means when your curl of the vector field is non-zero, then it reflects the rotation of the vector field, and you can know whether the vector field has a tendency to rotate depending on this term. So if the vector field does not have a tendency to rotate, then you will have the curl of the vector field equals to 0. So it means you will imagine that the vector field is just going straight in one direction. So here I borrow the picture that I took from the book by Boas, Mathematical Methods in the Physical Sciences, and this shows you a very nice examples of a vector field that is rotating and not rotating. So in this first example, which is A, this is a vortex, and in here you see this is, you have a field that is turning on this plane. And now if you ask yourself, whether is this a field which rotates or not, and you will see that if you evaluate the curl of the vector field like this, and you will find that these are not zero at the center. Okay, so at the center it is not zero, whereas in the example B, this is going to be a irrotational vector field, which means curl of the vector field is going to be 0. So when you have curl of the vector field equals to 0, then this is called an irrotational field. Now in the example number C, here they use the same example as B, but then they say you put a pedal, basically you are going to kind of like rotate it, So when you rotate it, then you will see, you have a possibility of the vector field here going faster than the one at the bottom here. And this, although the flow is going on the same direction, but then the magnitude is not the same. So here you have a tendency to rotate. So when you have a tendency to rotate, your curl of the vector is not equals to 0. Now what about this example? So let's say a vector field going through a corner, right? So is this going to give you a curl of the vector field equals to 0 or not? So it turns out that in this case, the curl of the vector is going to be equals to 0. Okay, so now we will ask ourselves why. So when you want to evaluate the curl of the vector, whether it is rotational or not, it basically depends on the neighboring area. So if you're talking about the flow of the vector over here, let's say at this point, given by my laser pointer here. So if you are talking about the tendency to rotate at this point, it is going to be evaluated based on its neighboring points. It is not going to be evaluated at that point, but at its surrounding area. So here, for example, you have here it is actually turning. It is actually turning, but the same goes with its neighbors. So they are turning on the same directions. So therefore, the curl of the vector at this corner is going to be equal to 0. And this is the same as the one in B, because this is going in the same direction. It's a straight line, and you have this equals to 0. But in this case, this is also the same. Although it's not a straight line, they are turning in the same directions and the same speed, right? So in this case, the curl is equals to 0. So then if you go to the book by Boas, there is a short discussion about the conservative field. And if you remember from our previous discussion, we say field is conservative if you go from one point to another and the integral gives you the same answer, right? So in this set of rules that you can find in the book, this is a more definitive set of rules that you can use, that you should use to evaluate whether a field is conservative or not. But then we will just leave it as it is, and I will encourage you to go into the book and try to understand it a little bit more. So now I'm going to talk about the rationale behind the Stokes theorem. Basically, why or how you can relate between the integral over an open surface with the integral over the boundary that connects this surface together, right? So let's take a look at this example. So here I have make a plot where this is the arrows here are my vector field. Okay, we'll talk about this vector field, but this is just an example. So this is a vector field, and this is my hemisphere, which is on the bottom half of the hemisphere. This is 0 and this is -1. So here we want to talk about the 3D Stokes theorem, right? So here, let's go. So here the right hand side here, you have an integral v dot dr. So this is basically an integral over this boundary here. So this circle over here, this is the boundary of this surface, right? So now when you talk about the right hand side, basically you're going to take the integral of this line around the boundary of the surface, right? So on the left hand side, you have a curl of the vector, and this you dot with n. So this n is the unit vector that is normal to the surface. So as you go from one point in the hemisphere to another point, the unit vector that is normal to the surface is going to change in directions, right? So here, in order to evaluate this integral, so let's talk about doing an integral over the whole surface, right? So now, if we take, for example, you have the chance, or you can actually slice the surface into half. So you cut it into half. And then now when you want to evaluate the integral over the area, right? Because on the right hand side basically it is integral with respect to the area initially. So here you have a d sigma here. So when you do that, you will see that I have two surfaces here, that if I cut them to half, I will evaluate the integral from here to here to here and here, right? So then the same with the other half of the hemisphere, the integral is going to be evaluated this way. Now you will see if you do that, these two lines, they are basically on the same boundary. Right? They are on the same boundary, but one is going upwards and the other is going downwards, and therefore this is going to cancel one another. So effectively, you are just going to have the contribution from here to here, that is at the boundary of it, right? So now let's cut the surface into smaller parts, even finer, and we will use this 4 squares over here to say that this is the boundary that I'm interested. So this is d sigma, right? And I'm going to evaluate the integral along this component, and basically I want to evaluate for the whole surface, so I have to do for the other remaining lines, right? So here I'm going to continue doing it to the box or to the boundary on the right hand side, and I will continue onwards, and you will see that this and this is going to cancel, and this one is going to cancel, right? So basically you have one big line here. But then the same can be said about the bottom half, where here you will see that this two line is going to cancel, and this two is going to cancel, this two is going to cancel, and if you repeat this process, basically they will all cancel out one another, right? The same with this, you see, because over here you have arrow going down, but then on the left of it you're going to have an arrow going up, so this is going to be cancelled as well. So at the end of the day, the only surviving term is the one that is over at here. Okay, and that is the rationale, behind the idea of integrating the curl of this into just evaluating the vector field along the boundary of the surface. Okay, yeah. So now let's look at the application of this Stokes theorem. So the first example that we will discuss here is the case of a hemisphere. So this is the opposite of just now. This is on the positive z direction. So now let's take a vector field that is given, for example, like this equation over here, and you want to evaluate the curl of the vector over the hemisphere, right, over this hemisphere, with a squared larger than 0. So let's talk about 3 ways to solve this. Basically, you have the very easy way, you have the slightly difficult way, and one more which is more tedious. But at the end of the day, these 3 ways are going to give you the same results.